so welcome back after the short break. So we are talking about the differential amplifier and we assume that we do have meaningful value of this DC voltage. So our next exercise is to find what may be the range, suitable range of this common mode voltage. So yeah, so let us see in the next slide. This slide I will skip. So here we are having some value of V in C, which is just 0.8. In fact, we need this voltage to be at least 0.6, because to make Q1 and Q2 on, we need the VB voltage sufficiently high. So here just we are taking 0.8, so that the drop across this resistance, it is only 0.2. So if the voltage here it is only 0.2 and RT it is 1 K, and the DC voltage here it is 0.8, which is given here. So the current flow here it is just 2.2 volt divided by 1 K. So that is 0.2 milliampere. Of course, strictly speaking, if we have say 0.2 milliampere current, and if we have a split of this current, and the emitter current it is say 0.1 milliampere, then VBE it will not remain at 0.6, it may be definitely lower than 0.6, maybe around 0.5. But just to say that even if it is a 0.5, the value of this current it is quite low compared to our previous case, where we considered current it was 1 milliampere. So, instead of going into the detail of what exactly be this current, but say this DC voltage here it is low enough, making this current it is small, and we like to see what is its consequence. So, if the IE current it is 0.1 milliampere, and hence we can approximate that IC1 it is also equal to 0.1 milliampere. So, same thing for IC2 as well, and then the drop across this resistance, which is 5.2 K. So, the drop here it is only 0.52 volt. So, the DC voltage here and here it is 12 volt minus 0.52. So, that is 11.48 volt. So, this voltage it is quite high. So, you may feel that once this DC voltage is closer to the supply voltage, the signal swing towards the positive side it is very limited. It will be only theoretically only 0.52. On the other hand, negative side we do have very good swing. It can go as low as 0.2 volt here, and then 0.5 VCE VCE SAT. So, that is 0.3. So, the lower limit here it is 0.5. So, if it is 0.5 here, the minimum value of the output voltage, then we do have very good swing of 11, close to 11 volt. So, negative side swing is not a problem, but the positive side swing it is very small, 0.52. So, that is the first problem. The second problem it is with this value of this IC, GM1 and GM2, they are now 0.1 milliampere divided by 26 millivolt. So, that is equal to 1 by 260 mho. So, of course, the resistance R O, they are also quite high. So, R O 1 equals to R O 2, both of them are 100 divided by 0.1 K. So, that means 1 mega ohm, but it is not having any influence on the gain, because the output resistance, it is dominated by this passive resistance. So, the differential mode gain A D, which is G M into R C, so that is equal to 5.2 K divided by 260. So, that is equal to only 20. So, the gain, you may recall the previous case when the current here it was 1 milliampere, the gain it was 200, now it comes to 20. So, naturally the signal, expected signal at the output, it will be quite small. So, what we are expecting that VOD equals to 20 multiplied by V in D, and V in D is 0.02 sin 2 pi by capital T. So, that is equal to 0.4 sin 2 pi by capital T into T. So, that is what I said, that amplitude here instead of 4 volt, now it becomes only 0.4 volt. Also, if you see the common mode gain, let me use this space, AC equals to minus Gm into RC divided by 1 plus Gm into 2RT, and the Gm we say that 1 by 260. So, the numerator it becomes 20, which we already have calculated, and here we do have 1 plus 2000 K divided by 260, and I have done this calculation for you. Let me look into it. So, I do have the common mode gain. It is not having much change. In fact, it is only minus 2.3 instead of minus 2.6. So, the common mode gain it did not change much, but the differential mode gain it has significantly changed. So, then now if you see the so due to this one VOC, it can be obtained by multiplying this 0.2 with 2.3. So, that gives us minus 0.46 sin 2 pi by 4 capital T into small t. So, that is the VOC, and then this is the VOD, and the DC voltage it is given here. So, from that you can find the individual signal, namely say VO1, I am doing only one for you. So, this is having a DC voltage of 11.48 volt, and then we do have this signal minus. So, this is a common mode signal minus 0.46 sin 2 pi by 4 capital T into small t, and then half of this signal, let me use different color here, half of this signal it is plus 0.2 sin 2 pi by capital T into small t. Now, if you see the magnitude for some time instance, the magnitude it will be 11.48 plus for some time instance we will be having 0.46. So, that gives almost close to 12 volt, and then we do have 0.2. So, in fact, if you add this amplitude and this one, it is exceeding this 12 volt, which is impractical. So, what does it mean is that at this point and this point, the signal combination of this common mode and differential, in fact, they are getting distorted, because the voltage here it cannot exceed this 12 volt, indicating that the DC operating point it is too high. In fact, you may recall the positioning the operating point with respect to the load line. So, suppose this is the load line defined by the corresponding RC that we have discussed for common emitter amplifier, and if the circuit is in good condition, then pull down element should be such that the operating point should be middle of this range. Now, in this case, since the current here it is too small, the corresponding characteristic curve of the transistor actually it is here. So, due to the small current, the operating point it is very close to that VCC supply. As a result, even if we do have a small signal, the signal it is getting distorted there. So, we need to be careful there. Okay. So, indicating that this voltage probably it is quite low, and it is alarmingly low, and the gain here it is very small, particularly the value of the GM it is small, and that is coming from the device it is almost in the I should say towards the cutoff. So, definitely lower this V in C, it will be having even more severe problem. On the other hand, let us try to see what may be the upper limit of this V in C. So, this is the exercise we can try. What may be the maximum value of this V in C, keeping both Q1 and Q2 in active region of operation, which means that we like to get the limiting case, namely if I increase this voltage, then what will happen is that this voltage it will follow the base voltage minus 0.6, and hence this current IRT increases, and if the IRT it is increasing, then drop across this RC called VRC1, that also increases, and since we do have fixed 12 volt, and if this drop it is increasing, so that will make this voltage decreasing. So, which means that if I increase the voltage here, the base voltage of transistor 1 it is going higher and higher. On the other hand, the collector voltage it is coming lower and lower, and there may be a situation where these two voltage difference it will be such that the base collector junction it may get forward biased. In fact, if it is weakly forward biased, then we may say that device it is entering into the saturation, and if it is strongly getting forward biased, then dip into the transistor it will be dip into the saturation region. So, to calculate the limit of this DC voltage where this transistor it is just entering to the saturation, what we can do, either we can compare this voltage and this voltage, or the better approach is that if we have the base voltage and then we take out 0.6 volt to get the emitter voltage here, and then we add VCE sat of 0.3 volt. So, then we can say that this is the limit of the collector voltage. Namely, if I consider, okay, let me clear this one. If I consider the this path in the limiting case, whatever the voltage you do have minus 0.6. So, V in C max minus VB1 of say 0.6 volt, then plus VCE sat of 0.3 volt. So, that is equal to the collector voltage, and then if I add this voltage, so that is RC into whatever the IC, corresponding IC called say IC max. So, that is equal to 12 volt. In fact, if you consider this voltage in the limiting case, this is equal to the emitter maximum voltage, and this voltage it is RT multiplied by 2 times of whatever the collector current we do have, approximating that collector current and the emitter current, they are equal. So, if I rewrite this equation, what we are getting here, it is 2 times RT into the limiting current IC max plus RC1 into IC max equals to 12 volt minus this 0.3. And as I said that this 0.6 it is VB1 and this 0.3 it is VCE saturation limit. So, we know the value of this RT, we know the value of this RC1, and so we can calculate what is the maximum value of IC called IC max. So, that is equal to 11.7 divided by RC is equal to 5.2, and this is 2 K. So, this much of milliampere, and this gives us I think I do have calculation for you. I was getting IC max, it was 1.625 milliampere, and this current, it is creating a drop here, which is 2 times of this current multiplied by this 1 K. So, the corresponding drop here or the emitter voltage here, it will be 3.26. Now, if I add this 0.6 volt here to get the corresponding maximum voltage of V in C max, so that becomes equals to 0.6 and 3.26. So, that is 3.86 volt. Okay. So, this is indicating that if I put this limiting case, and again if we recall the load line and the operating point concept, ideally we like to keep the device in this region, and the operating point should be almost at the middle of the possible range. And in this case, if I consider V in C max, the corresponding device characteristic, it is going towards the extreme, namely it is going somewhere here, and keeping the device, it is just at the saturation limit. So, this is corresponding to V I in C max. and this is the maybe some nominal case, and other case we already have discussed that if on the other hand V in C it is approaching towards 0.6, then the characteristic curve it will be like this. Okay. So, that gives us the range of V in C. So, while we will be designing this circuit, we have to keep that in mind, and since we do have passive resistor here, so the operating point it is very much dependent on this V in C. If we do have active device, probably then dependency of this current it is not so so much on V in C, but again V in C definitely it will be having a suitable range. So, once we see some numerical example there, probably we can discuss the range of the V in C. Now, coming to differential amplifier realized by MOSFET and going back to the similar exercise. Yeah, so here we do have differential amplifier realized by MOSFET. It is very similar to BJT, but of course, the IV characteristic here they are different. So, again let you consider a meaningful value of the input DC voltage of 4 volt, and different parameters are given. Both the transistors are identical, having transconductance factor of 2 milliampere per volt square. Threshold voltage of both the transistors are 1 volt. Lambdas are given here, and then RD1 and RD2 they are identical, and both of them are equal to 4 kilo ohm. Supply voltage it is 12 volt, and again RT we are considering 1 kilo ohm, and this load capacitance is in this example it is not really having much significance. Now, coming to how we find the differential mode gain and common mode gain, first of all we need to start with the operating point of the transistor. So, we do have a DC voltage at the gate which is equal to 4 volt. Now, if we have a 4 volt and then it is probably it is having some VGS here, whatever you say VGS1 or VGS2, and here also of course we do have 4 volt, and the voltage here of course depending on this DC voltage divided by this RT, it produces a current of IRT. And again because of identical transistors M1 and M2 and RD1 and RD2, and the currents are getting equally split into 2 branches. So, this is IRT by 2 and so and so. So, if I consider this loop and if this voltage is given to us, from that we can find what will be this current, or we can say what will be the corresponding IDS current of transistor 1. And so let us try to see the for this voltage what is the corresponding IDS. First of all, this IDS equals to this K W by L by 2 into VGS minus VTH, whether it is for transistor 1 or transistor 2 they are equal and square. So, we are ignoring this 1 plus lambda VDS part, right. So, we consider 1 plus lambda VDS part, it is approximately equal to 1. So, here we do have the second order equation, and also the current flow here it is 2 times of IDS. So, we can say that V in C minus VGS, whether you call VGS 1 or VGS 2. So, that is equal to 2 IDS times R t, right. And then expression of IDS, it is given here. So, what you can do here, it is we can write this K n W by L VGS minus VTH square into RT. Now, we do have VGS 1 here, and of course, we do have VGS 1 here, but we do have VGS 1 minus VTH square. So, we can probably directly we can try to solve and try to see what is the VGS 1, or maybe a better way to convert this VGS 1 in the form of VGS minus VTH. What we can do? We can take V in C minus VTH 1 and then minus VGS 1 minus VTH 1 equals to K n W by L into VGS 1 minus VTH square into RT. Now, this equation here, if you see this term, particularly VGS 1, it is not known to us. So, we can say that these two terms we can say x, rest of the things are known to us. So, this is 4 volt minus 1 VTH is 1, and let you call this is x equals to, this is given as 2 milliampere per volt square. So, this is x square, in fact, x is a unit of x is volt, and then RT it is 1 kilo ohm. So, that gives us x square, in fact 2x square plus x minus 3 equals to 0, and from that you can get x equals to minus 1 plus minus square root of 1 minus 4 into minus it gets plus, and 3 into 4 into 2. So, that is giving us 24 divided by 2a. So, that is yeah. So, we do have 4 here. So, here we do have minus 1 and then plus minus. So, this is 25, that is 5 by 4. Obviously, minus 1 will not be considering because that is not the practical value. So, we will take plus 1 and this is equal to 1. So, this x is equal to, actually x is equal to 1 volt. So, that gives us the this VGS equals to VGS minus VTH is 1 volt, and hence VGS equals to 2 volt. And in fact, from that here we can say that IDS equals to, this part it is 2 milliampere per volt square, this part is 1 and this is 2. So, that gives us IDS 1 equals to 1 milliampere. Good. So, we got this IDS equals to 1 milliampere. So, the current flow here it is 2 milliampere. So, that gives a drop here, it is 4K multiplied by 1 milliampere. So, that is the 4 volt drop. So, we do have 12 volt supply minus 4 volt. So, that gives the DC voltage here it is 8 volt, and this is also DC voltage of 8 volt. Now, we can see that we do have at the gate we do have 4 volt and at the drain we do have 8 volt. So, that is good for this transistor. The transistor it is well within its saturation region of operation. So, we obtained, so far we obtained the operating point and then DC voltage you also obtained. Now, we can calculate GM. So, GM1 it is for a given value of the VGS 1 is equal to 2. So, from here we can calculate GM1 is equal to Kn W by L into VGS minus VTH, and that is equal to 2 milliampere per volt. Same thing GM2 also, and RDS equals to both RDS1 and RDS2, that is equal to 1 by this lambda, it is 0.01 into 1 milliampere. In fact, that gives us 100 kilo ohm. So, that is how you obtain the small signal parameter of the transistors. And swing wise, on the other hand, swing wise, if we have 8 volt DC, and then positive side we do have 4 volt swing, and negative side on the other hand, if the gate voltage it is 4 volt and threshold voltage it is 1 volt. So, the minimum voltage at the drain it is 4 minus 1, that is the 3 volt. So, lower limit it is 3 volt. So, the possible swing here it is 8 minus 3 volt. So, that is the 5 volt negative swing. So, the positive swing it is 4 volt and negative swing it is 5 volt. So, it is having very decent amount of signal swing. Now, coming to the gain, GM it is 2 milliampere per volt. So, that gives us the differential mode gain AD equals to GM1 into RD. So, this is 2 milli multiplied by 4K. So, that is equal to 8. And on the other hand, the common mode gain, okay, let me erase some part of it, otherwise the board looks very clumsy. So, the common mode gain, so what we said that AD we obtain equals to 8 and AC is equal to minus GM into RD divided by 1 plus GM into 2 RT. So, this part it is already we obtain 8, and on the other hand here we have 1 plus GM it is 2 milli, and this is 4 2K. So, this part it is 4, this is 1. So, that gives us minus 8 by 5. So, the differential mode gain it is 8 and common mode gain it is minus 8 by 5. So, as anticipated that the differential mode gain it is not so high because of the MOS transistors, they do have relatively lower value of GM, but whatever it is. Now, let us see that what kind of signal we do get at the outputs. So, again let you consider these two signals and let you consider it is mixed mode of operation, namely at the input we do have both differential as well as common mode signal. So, in the next slide, yeah. So, here we do have Vin 1 and Vin 2. Again here it is having the differential signal and the corresponding common mode signal, and you may recall that the AD equals to 8 and AC equals to minus 8 by 5. Okay. Now, for simplicity of calculation, let me consider this common mode part, it is 0.5 instead of 0.3, as the common mode gain it is minus 8 by 5, since we do have 5 in the denominator. So, let me consider 0.5. So, the differential signal at the input V in D equals to 0.5 sin 2 pi by capital T into small t, and on the other hand the common mode V in C equals to 0.5 sin 2 pi by 4 t into small t. Note that since the gain, differential mode gain here it is low, intentionally we are taking relatively higher value of the differential input compared to the case when you talked about differential amplifier using BJT. So, both differential part and common mode part, they have equal amplitude. Now, using this information, we can say that VOD equals to 8 multiplied by this 0.5. So, that gives us 4 sin, let me use different color for consistency, VOD equals to 4 sin 2 pi by capital T into small t, and the common mode output VOC equals to now this 5 and this 5 it is getting cancelled, we do have 8 in the numerator. So, that gives us 0.8 sin 2 pi by 4 t into small t, right. So, if I combine these two, we can get the individual signal, and as I said that individual signal they do have a DC voltage of 8 volt. So, VO1 it is having a DC part of 8 volt, and then plus common mode part it is minus 0.8 sin 2 pi by 4 capital T into small t, and then half of the differential part. So, that is plus in phase with this differential. So, that is plus 2 sin 2 pi by capital T into small t. So, likewise the other output VO2 it is having a DC part of 8 volt, and then it is having the common mode part of 0.8 sin 2 pi by 4 capital T into small t, and then minus 2 sin 2 pi by capital T into small t. Now, again here you can see that the since the differential mode gain and common mode gain they are different. In fact, common mode gain it is 1/5 of the differential mode gain. So, as anticipated that the signal at the output, if I consider difference of these two, it is having a differential mode signal of 4 volt amplitude, and common mode part, unwanted part, it is having 0.8. Of course, it is getting reduced, but still it is not clean. The differential part it is still it may get affected by this common mode component. So, we need to do some modification of this circuit. Either we can try to increase this voltage gain or differential mode gain, or we can try to decrease this common mode gain, or maybe combination of both. We can try both, increasing the differential mode gain and decreasing the common mode gain. In fact, if you see the expression of the common mode gain, this RT or 2 RT is having important role to play. So, to decrease this resistance, what we can do? We can replace this resistor by say active device. So, in our example, what we will be doing? We will replace this resistor by an active device, and then we will see what may be its corresponding consequence. And in case if you want to increase this gain, we can replace this 2 passive resistor by active load. So, that example probably some other day we will see, but today definitely we will be replacing this passive element by active element. So, before we go into that, we can also like to see what may be the suitable range of this input common mode voltage. In fact, if you consider threshold voltage of the devices, it is 1 volt. So, definitely the theoretical limit of V in C, it is lower limit is 1 volt, but to have some current, the voltage here should be beyond that. So, let you consider the voltage here, it is say 1.12 volt, and try to see what is the corresponding current. So, in the next slide, what we are considering, that V in C, it is 1.12, and if you consider this is 1.12, and the method we have followed to find the corresponding current, it can be followed, and it can be shown that the current here it is 0.1 milliampere. So, these two currents are 0.1 and 0.1. So, that gives us the voltage here, it is 0.2 volt, right, and no, this is 1.2. So, sorry, this should be 1.21. So, if I take 1.21, we will be getting a meaningful value here. Yeah, and then VGS minus VTH. Okay, I think the numerical value I have taken here, it is not so accurate to get a round of current, but just I like to say that in this case again here we do have a meaningful range of V in C. So, if we do have higher and higher voltage, then that may increase this current, and that may increase the voltage drop here, and hence it may push this transistor M1 into triode region. So, we can probably find what may be the corresponding upper limit. So, upper limit is very important for this case. Lower limit, definitely we do not want to keep the transistor more towards the subthreshold region, definitely not, but we should be aware about the upper limit. Okay. So, due to the this question, it will maybe, or this numerical problem, it will be similar to the previous one. We will skip that part, and in the next problem what we will do, we will replace this resistor by active device and try to see what may be its corresponding consequence on the common mode gain and differential mode gain. So, in the so here we do have a differential amplifier, and also I must say that in this circuit, this is the first time we are trying to combine both MOSFET and BJTs together within one amplifier, and this is of course intentional, just to give you a confidence that you can mix BJT as well as MOS in your circuit, as long as you are following the fundamental basic guidelines, then you can mix it properly. So, here as I said that this RT, earlier we used to use RT, that has been replaced by this device. In fact, if you see the device characteristic, you may see that it is almost working as one ideal current source, but it may be having some finite conductance, and this conductance or inverse of this conductance is basically RO1. Now, what is this current? This DC current can be obtained by considering its base bias. At the base we do have RB1 and that is connected to 12 volt supply, and RB1 its value it is given, it is 570 K, and if I consider VB equals to 0.6, then from that we can get IB equals to, so IB1 equals to 12 volt minus 0.6 divided by this RB, that is 570 K. So, that is equal to 20 microampere, and then we do have beta equals to 100. So, the corresponding current here it is 2 milliampere. Now, since the left branch and right branch they are identical and we do have equal DC voltage coming there V in C. So, we can say that in both the transistors IDS equals to 1 milliampere. And again, so this biasing condition it is such that we are retaining the output DC voltage. So, we do have 4 volt drop across RD1 and RD2, and then we do have DC voltage of 8 volt. So, we do have 4 volt here, and now this current is in fact it is more dependent on the lower transistor rather than this voltage. In fact, it can be shown that even if say this voltage it is rising and hence this voltage it may be rising, but since this transistor it is in active region of operation, its current it is predominantly defined by its base current and the beta. So, the tail current it is remaining same as 2 milliampere. So, I should say the DC operating point here it is not really much dependent on this voltage, unless we are making this voltage it is very small and forcing the source node very low, pushing this transistor Q1 into saturation. So, as long as that is ensured, then we can say that both this current and this current they are remaining 1 milliampere. And to get that, we can say that V in C, if it is higher than, let me clear the board. So, we can say that if V in C it is higher than the required 2 voltage here and VC is at 0.3, then we can say that the current here it will be 2 milliampere and current here it will be 1 milliampere. So, as long as V in C is higher than required 2 voltage to support 1 milliampere of current plus 0.3 volt the V C is set. So, this is VCE set and this is the required VGS to support IDS equals to 1 milliampere. Now, if this V in C, as I said, it is higher and higher, it will not create any problem. In fact, if this voltage it is rising, the voltage here it is still remaining at 8 volt. So, so of course, this is the lower limit of V in C. So, likewise, if this is 8 volt, the upper limit of V in C on the other hand, it can be obtained by considering the limiting case when transistor 1 it is just entering into the triode region. So, when will it be in triode region? V in C max, once it is reaching to a value where this transistor it is entering into triode region from saturation, and that time this is 8 volt and the corresponding voltage here it will be 1 volt higher than 8 volt, that means this is 9 volt. So, V in max it is 9 volt. So, in summary what we can say that V in C it is having a nice range. The upper limit it is 9 volt and lower limit it is 2.3 volt. Of course, this upper and lower limit they depends on how we are setting this current and what is the value of this resistances, and of course, to support this current what is the required VGS, basically this part. Okay. So, now in this circuit at least we do have better definition of input common mode range or better limit, strict limit of the input common mode voltage. Now, if we are keeping this V in C within this range, as I said that the current is not changing and so is the DC voltage, it is not changing, and also since the current flow here it is remaining 1 milliampere, the corresponding GM it is also remaining very close to 2 milliampere per volt, and the corresponding gain it is remaining close to this 8, right. And in case if you are placing a resistor here, of course, the corresponding current depends on the V in C, and hence the corresponding GM will also be changed, and then of course, the corresponding differential mode gain. So, that is the advantage of having this active tail resistor. The biggest advantage of having this tail resistor it is we yet to discuss is that the corresponding common mode gain. In fact, let us try to see what is the corresponding common mode gain. So, to calculate the common mode gain, we know that in the expression of common mode gain we do have GM R D, and in the denominator we do have 1 plus 2 GM into RT. Now, while we do have this active device instead of passive element, whatever the R naught we do have, that is playing the role of RT, because if I consider its small signal equivalent circuit out of this tail current source, where this part is the DC, and for DC of course, we have to remove this part, and then we will be having this RO1 it is left behind in the small signal equivalent circuit. So, RO1 it is essentially playing the role of RT. So, it is now intuitive that common mode gain it becomes minus GM into RD, GM1 or GM2 both are same, RD1 and RD2 they are also same, and in the denominator we do have 1 plus 2 into Gm into this RO 1. And if you see its magnitude, RO 1. So, RO 1 if I consider its early voltage of say 100 volt and its current flow it is 2 milliampere. So, that gives us its RO 1 equals to 100 divided by 2 kilo. So, that is 50 kilo ohm. So, the value of this common mode gain it is equal to numerator part it is we already have calculated 8, and the denominator part we do have 1 plus this is 2 into then 2 and then 50. So, that is 100. So, that is equal to minus 8 divided by 201. So, we may approximate this by 200. So, that is equal to minus 8 divided by sorry, this is equal to 1 by 25, which means that if we apply say same signal, this differential and whatever the common mode signal we do have as we have discussed earlier, let me consider this is 0.5 and 0.5, and there what we have seen is that the common mode signal it was quite prominent. It may not be higher or equal to the differential part, but at least it was quite prominent. But by replacing this passive element by this active device, since now we are getting common mode gain it is 1 by 29. So, that gives us the VOC equals to 1 by 25 multiplied by 0.5 sin 2 pi by 4 capital T into small t. In fact, that gives us very small common mode. In fact, this is 0.1. So, this is 0.02 sin 2 pi by 4 capital T into small t. On the other hand, the differential part since the differential mode gain it is remaining 8. So, AD equals to Gm into RD. So, that remains 8. So, this differential part on the other hand it remains same as what we have seen, it is 4 volt. 4 volt. So, the differential part, let me use a different color for that, pink color. Yeah. So, VOD on the other hand it is 8 multiplied by 0.5, difference of these two 0.5 sin 2 pi by capital T into small t. So, then if I combine say this differential signal and common mode signal, since the common mode signal is very small compared to differential part, then individual signal they will be very close to fully complementary to each other. So, we can say that VO1 it is almost equal to 2 sin 2 pi by capital T into small t, and the VO2 it is very close to minus 2 sin 2 pi by capital T into small t. So, to summarize, replacing this tail it is also helping to suppress this common mode part and still maintaining the differential signal quite prominent, particularly if you observe the output, the signals there, it is almost like complementary to each other. I think we do have covered whatever we have planned today. So, as I said that the small signal equivalent circuit and analysis, those things it has been done in our previous lectures, and in today's lecture primarily we have focused on numerical examples, mainly with extensive calculation on differential amplifier using BJT for calculation of the operating point, then differential mode gain, common mode gain, then range of the V in C, output swing, and also we have seen that what are the different outputs are there, and same thing we have done quite an extent for the differential amplifier having MOSFET, and then we also have discussed about the differential amplifier having both MOS and BJT. Particularly what we have seen is that even though this differential amplifier, its gain it is not so high, differential gain it was only 8 in our example, but by replacing the tail resistor RT by active device 1 NPN transistor, that helps us to really suppress the unwanted common mode signal quite an extent, and ensuring that at the output we are getting almost complementary signal. I think that is all to share. Thank you for listening.